Kia ora Year 12. In this video, I'm going to do 4 of the merit questions from last year's integration paper, and I'm going to want you to pause the video as I show each of the questions at the start so that you can have a go at them if you haven't already got them from the website. So 1b is one where we're given the gradient function of a curve and it goes through a point, and we have to find, first of all, the equation of the curve. Now, I think that this part here is just the achieved part of the question, and then in the next part, we have to find the area enclosed by the curve. So that's the curve that we've just found up here, the x-axis and these 2 lines. So there's something you just have to watch out for in that question that I want you to have a think about. Then 1c is a kinematics question. So it's just like a level 2 kinematics question. We're given, what are we given? We're given acceleration. This is it here. And from there, we have to work through to find displacement of an object after 5 seconds. The only thing that makes it harder than a level 2 question is that we've got a trig function to work with. And actually the setup of the question is much more straightforward than some of those wordy excellence level 2 kinematics problems that can get a little bit messy. Then we've got question 2, and question 2c is to find this definite integral. So this is a trig product. Massive hint for you. If you go to your formula sheet, hopefully you realize that this is problematic to integrate straight away. So we're going to want to use something from down here, and that's going to make it a pretty easy thing to work with. Lastly, in this video, I think I'll get time to do all 4, is this merit question where we've got the graph of this function here, and we're told that the shaded area has an area of 4. We have to find the upper limit of integration. So I think that's a very, it's very clear in that question what you've got to do, hopefully. Just a little bit of algebra work. Okay, so going all the way back to 1b, let's look at what we've got. Well, we've got the gradient function. So f dash of x is equal to 8x to the negative 3. So f of x or y will be 8 times x to the negative 2 times 1 over negative 2, doing backwards chain rule, plus c. So that gives me negative 4 over x squared plus c. We're told that the curve goes through the point 1, 3. So that means I've got 3 is equal to negative 4 over 1 squared, which is 1 plus c. So c is equal to 3 plus 4, which is 7. So my function here is y is equal to negative 4x to the negative 2 plus 7. So that's the first part. And in the next part, we have to find the area enclosed by the curve, the x-axis, and the lines x equals 1 and x equals 2. Now, it's well worth throwing that into your graphics calculator and seeing what we get. Obviously, we're going to have an asymptote at x equals 0, right? Because my curve is negative 4 over x squared plus 7, so I can't have 0. And it's going to look like this. The question that we need to answer before we start is to just think about whether 1 and 2 are on different sides here, or whether they're on the same side here, because we're going to have to watch out if we're finding the area under the curve. If we've got a crossover point halfway, we're going to have to find the absolute value of that integral and add it to that one. So if you have a look at your graphics calculator, you'll see that the crossover value here is going to be lower than our 2 values. So just putting that back in, if you think about what's going on here, if we put in x equals 1, we've got negative 4, that should be a plus. So negative 4 plus 7 is 3. And then we've got negative 4 over 2 squared plus 7, which is 6. So that means that there's nothing special, really, nothing hard about finding this area, because it's all, the y values are both positive. So this is what I'm looking for here. And actually, if you didn't do that in this question, nothing would have gone wrong. But in general, when you're looking at areas under curves, you just need to take a little bit of care. Okay, so here we've got the integral from 2 to 1 of negative 4x to the negative 2 plus 7 dx. And that equals 4x to the negative 1 plus 7x between 2 and 1. So subbing in values here, I get 4 over 2 plus 14 minus 4 over 1 plus 7. What do we get here? We get 16 minus 11, which equals 5. All right, on to question 1C. This is our kinematics one. We just want to make sure that we show what integration we're doing in here. So v of t is the integral of 2 minus sine of 2t. We're trying to work our way up towards displacement. So we're starting at acceleration and we're going to integrate. We get 2t, and then we're going to have cos of 2t. When we differentiate this, we get a 2 popping out, so we need to undo that with a half. The integral of cosine is negative sine, so in here we want to have a plus sign, and we need a plus c on the end. We know that the initial velocity is 1 meter per second, so we've got 1 is equal to 0 plus a half of cos 0 plus c. Now cosine of 0 is 1, so we get 1 minus a half is equal to c. C is equal to a half. So v of t is 2t plus a half cos of 2t plus 1/2. So that's the first part of the question done. From here I need to work out the displacement. So we're going to integrate again. So s of t is equal to this integral. Working backwards, we're going to get t squared plus, now we'll put in a half. Cosine has come from the sine function, so when we differentiate the sine function, we are going to get positive cosine, so that's good. But again, we're going to get a 2 popping out in our chain rule differentiation. We undo it by timesing by a half. Next, we've got plus 1/2 of t, and then we've got another constant. I'm going to call it k. We've got t squared plus a quarter sine 2t plus a half t plus k. So that's my displacement function. And we're told that after, at the start, t equals 0, it's got a displacement of 3. So we can sub in 3 on the left-hand side. So 3 is equal to 0 plus a quarter of sine 0 plus a half of 0 plus k. So k is equal to 3. And that gives me s of t is equal to t squared plus a quarter sine of 2t plus a half t plus 3. Now I have to sub in t equals 5. After 5 seconds, we've gone 25 plus a quarter of sine 10, which is not an especially nice number, plus 2.5 plus 3, so plus 5.5. This is negative, so overall we end up with 30.364, which I've rounded to 30.4 meters to 1 dp. Right, question 2, sorry. Question 2 merit. Well, I've given you a big hint for this one already, so this should be really fast. We can't integrate this easily, so we're going to use our sums to product rules. We know that 2 times sine is equal to this. So that means that sine A sine B is equal to a half times cos of the difference minus cos of the sum. So that's what I want to use here. So we get this. It's equal to 1/2 times the integral from pi on 8 to 0 of cos of the difference. So 6x minus 4x. 6x minus 2x is 4x. And 6x plus 2x is 8x. So now we've got a very, very simple trig integral. We'll just get rid of this and work it out down here. So my integral is this. It's 1/2 of 1/4 sine 4x minus 1/8 sine of 8x between pi on 8 and 0. So just be careful substituting in your limits. You've got 1/2 of 1/4 of sine of pi on 2 minus 1/8 of sine pi minus, now we know that sine 0 is 0, so it's going to be minus sine of a quarter of 0 minus 1/8 of 0. In this case, the bottom limit being 0 does knock everything out. Just remember, in general, be really, really careful when your bottom limit's 0. If you're working with anything interesting, like a cosine function or an exponential, it's not all just going to go away. But happily for us, in this case, it nearly all does. And here we've got 1/4 times 1, and here sine of pi is equal to 0. So my final answer is simply 1/8. Right, on to 2D really quickly, because we're up to 10 minutes already. Right, we've got a function here, which is g of x. We've got an area under a curve, and we have to figure out what this limit value is. So this is what we're solving. Oops, dx is equal to 4. Integrating the left-hand side, I can see that I've got 6 is equal to 3 times 2. So here we'll have the natural log of 3x minus 4 times 2, evaluated at k and 2, right? So where this is coming from is that the log of 3x minus 4 will give me 1 over 3x minus 4 times the derivative of the inside function, which is 3. I don't want 3, I want 6, so I have to times it by 2, and that equals 4. I'm going to take this constant through and have this. So dividing through by 2 on both sides, and then I get the natural log of 3k minus 4 minus the natural log of 6 minus 4, which is 2, is equal to 2. Now someone's going to ask me how I know that I can drop the absolute value signs. Well, looking up here, we know that k is bigger than 2, right? So you don't really have to think this through this hard, but k's got to be bigger than 2, which means that 3k's got to be bigger than 6, so this is always going to be positive anyway. Now we get the natural log of 3k minus 4 is equal to 2 plus the natural log of 2. So 3k minus 4 is equal to e to the power of all that. I can split that up into e squared times e to the power of log of 2. And that gives me e squared times 2. You actually weren't asked for an exact value here, so if you didn't see all of this, that's fine. You can just do it in your calculator. But anyone watching this from my class who's doing A-level, you should absolutely be able to do exact values here. So 3k is going to equal 4 plus 2e squared. So k will be 4/3 plus 2/3 of e squared. So that should get a big tick. And the decimal approximation of that is that k is equal to 6.26, and that's to 2dp. So there you go, that's 4 merit questions done. There are a couple left from question 3. I'm going to do those next, and then I'll get on with the remaining excellence problems.